will follow this rule. So later on, we need to take a look at the model assumptions. First of all, we need to make sure that the model we applied here, we fitted here, is the correct one. Yeah, and you see, this is exactly the problem when I need my x11 function, because this window is too small. I could simply make this window a bit larger. So do you see any problem here? So do you like the residuals? Yes, no?
They don't satisfy the normality assumption.
Yeah. So they look, yeah, sorry, just finish.
And they don't seem to satisfy the scatter. They don't look good at all. Nothing looks good.
I mean, without knowing too much about statistics, right? If you take a look at our previous models, should I just? I'll just run it again. I mean, the pattern we have in the new model is completely different, right, than the residuals we had before. Meaning that here we use the wrong model to test this hypothesis. Because if you can remember, the data we are working with, they are binary data, binomial data. So basically you have zeros or ones, right? And such kind of data, they do not follow, well, if you fit a simple linear model to such kind of data, of course, the error will not follow normal distribution. Right, back to my guide. Again, you can look it up. We are dealing with binary data. These are basically yes or no events. Well, either species has dormant seeds or not. Therefore, we have to use a GLM with a binomial family, and this is how I specify this model. Right, again, the same question here. I expect that dormancy status is affected by elevation. I specify the type of data I'm working with. And the output looks more or less the same. The problem here, however, that the standard basic function here doesn't really work with GLMs, right? Because we use a very different set of rules here. But luckily for us, there is a solution called Dharma. It's a package developed by Florian Hartig, who is accidentally sits just, 2 rooms further in the corridor. And what the package does, so basically it simulates residuals and provides a kind of familiar output here, checking the assumptions for the generalized linear models. And again, about assumptions, so like I said, the assumptions we were discussing this morning, the 10 of them, do not really apply here because GLM work differently. Well, first of all, the data, the predictors particularly use, they should be independently distributed. This is always the case when you deal with ecological data. Well, the homogeneity variance, the shot in a wall does not necessarily to be satisfied, because in many cases when you deal with binary data, for example, it won't be possible, right? The errors need to be independent from each other, but their normal distribution is not the assumption. This framework uses slightly different algorithm to estimate the parameters, the estimates. And very important note here that this algorithm relies on large sample approximations. So basically, if you want to get a good model, if you want to get a strong fit, you require comparatively large sample sizes, right? Because, to provide the model with more data to answer your questions. But basically what is, again, without talking too much statistics, what you need to see or what you should not see here, well, first of all, the cuckoo plot, the residual should be aligned along this red line. This is actually the case. Here, there's black lines. Well, the line should be black and they should be parallel to the x-axis. So you see that actually only here we have some problems with the residuals, which is quite fine based on my experience. So the model outputs, diagnostics might look like even worse. You can also check, the manual for the package. He provides a number of examples how, bad fit might look like and a number of possible solutions. But like I said, you should not see any, so residual should be located along this line, and those lines should be black, which is quite fine. So we have now, we can make sure that the model we selected is correct to get a fit. But unfortunately for us, our hypothesis that seeds at high elevations tend to be more dormant as compared to lowlands. Well, the answer is no, it's not the case. Right, are there any questions on that?
So, how do you interpret this Dharma plot? Like, would you go on? Would you not care about that red line?
Yeah. Well, so one option would be, and this is actually always the case. So probably you're missing a predictor, which explains the variability in the dormancy ring. An option here would be to account for nonlinear effects by including this quadratic term. Oops. Now it doesn't really make it better, but this, for example, how a bad fit might look like, right? You see, we have more curves here. I mean, they still follow more or less the proper pattern. One option would be yeah, so maybe our data set is too small, to get a proper fit. So basically we have 70 species only, but based on my experience, I would just proceed with this model. Because like I said, it's not a beauty contest. And of course, you will have some deviations, from the best case scenario. But the most important fact that, the cuckoo plot looks normal.
So actually the QQ plot is comparing the residuals. So the residuals that you get when the model is correct should be uniform on 0, 1.
Yes.
So this QQ plot is comparing a theoretical uniform distribution with the those simulated residuals. So yeah, and the second plot on the right is looking at the distribution of the residuals at different predictions. So this plot on the right looks very similar to the upper left plot in your normal distribution. So, but there's a few differences. So the model predictions are rank transformed as opposed to just being the actual model predictions. And so we're looking for just noise, this sort of up and down noise, and they're trying to show you how these points should be distributed. So yeah, so ideally, again, you want the those grade lines to be parallel and to sit together with the dotted lines. But I mean, I agree with you, Sergey. It's a difficult, when do you reject a model and when do you not reject a model? It's not an easy call. I think what's important, though, is that all of this be very transparent, so that somebody who might not agree with you would be able to see what you did. So those distributions are not particularly good for low predictions. They tend to be a little bit on the high side.
Yeah, I think I have to confess that for the further workshops, I probably we need to show, let's say, some really bad examples. Let's say some good examples, just to provide, just basically give participants an idea how, bad fit might look like. Yes,
but I think that the idea of Dharma is to provide residual plots that look similar to the normal residual plots. So that's what these guys are trying to do. The guy on the left is trying to emulate the QQ plot in your plot function, and the guy on the right is trying to emulate the fitted relative to residuals.
So from my experience, I have to say that the plot on the right side has, well, if you get some problems like that here, so usually it's related to the predictors of your model. So either you miss an important one, either you included the wrong one, either they are autocorrelated. You might also consider to make some, here we go, some transformations to improve it, right? For example, it might be that some elevations are underrepresented in our data set. It's still, well, doesn't really make it better, but this would be an option, just, to play with the variables, try to transform them. So maybe it's not elevation, but so let's take a look what data we else have. It could be seed mass, right? Let's include it into the model. No, it makes it even worse. So. Yeah. Anyway, yeah. I mean, for the starters, I would say just, make sure that nothing is red in the plot on the right side, and whether the cuckoo plot looks fine. Right. Are there any other questions on that? I mean, the developers of Dharma wrote a very extensive, very long manual, how to use it, how to apply it to different kind of GLMs. Please read it. We also provide some information on the mathematics, how we calculate everything. Right. Now I think I have the last example for today. Oh, good in time. I'm going to delete it. The good thing about this GLM approach is that it deals with a number of, well, with this data in very different formats, right? Counts, proportions, probabilities, and so on. And when you're familiar with this approach, you can actually solve some old, well-known methodological issues in seed ecology and biology. So the next example is about logistic or binomial regression. So basically, it's a function, logistic function you probably know from the school. And basically, it estimates the probability of an event between 0 and 1, right? And basically, it fits, this curve to your data, and it estimates the probability of an event under given conditions or circumstances. And in this particular example, so we have a the species Anthoxanthum alpinum. You probably, where was it? Was it full? Remember it from, yes, from this example. So where we have 6 different test temperatures, 8 replicates, and we germinate the seeds and count them at different days and then calculate germination percentages. So in this particular case, you have 8 replicates with something like 25 seeds each. So in this case, I had a lot of seeds to deal with, but quite often, especially if you deal with protected or threatened species, you don't have, hundreds or even thousands of seeds to waste. And this is basically a small part of this large data set. Just imagine a situation where you have, well, species, the protected one is you don't have a lot of seeds, but you still want to find out whether seed germination of the species is affected by temperature, right? Instead, 8 temperatures, you have 2 replicates only. So what you would do probably, this is our data set, how it looks like, right? 1 species, 6 test temperatures, 2 replicates. So for example, here 24 seeds were sown and only 7 of them germinated. And now I want to find out whether temperature has any effects on it. Right, I calculate final germination percentage here, which is simply, this column divided by this column and multiplied by 100. So final germination percentage and this replicate would be 29%. And I start with our old friend LM. I fit the model, temperature is a factor. I get some results. Almost all of them are significant. I take a look at the residual plots. Yeah, everything looks more or less fine. But do we see any problems with this particular data set? I mean, would you trust your model? Would you trust those outputs?
I think one problem is that for those very high germination, there's very little variation.
Yes.
So the variation is decreasing as you get to very high germination percentages. So I think you would worry about this assumption that the mean and the variance are independent from one another.
Yes, correct. But I mean, the question has actually nothing to do with the statistics. Now I would like to, to appeal to your experience. I mean, many of you have been working with seeds, with any other objects. And in this particular data set, in this experiment, I have 2 replicates per temperature only. And if you remember, basically, we always need more data points, right? Or sufficient number of data points, amount of data to get the proper model fit.
But Adrian discussed this issue of that each row represents a dish. Mm-hmm. Those are not independent replicates.
Well, okay. What I'm driving at, so my point is that you have just 2 replicates per temperature, right? Basically, per replicate, you have one output only, final germination percentages here. And I think that, this amount of data is not really sufficient enough, to fit the model. So one option here would be to switch from germination percentages, from those data, from proportions, to binary data. I'm going to do some coding here. And now our transform data look differently. So what I did here, example, I had 24 seeds sown in the petri dish at the beginning of the experiment, and only 7 of them germinated, right? So another way of using this data, so I have 24 seeds in a Petri dish. Right? And 7 of them germinated. And the remaining 17 did not, right? So this is basically another way to look at your data. So instead of using averages per Petri dish, I move from proportions to binary data.
But this is the discussion that we had this morning with
Oh,
Adrian.
sorry, I missed it. Yeah.
Yeah. So, and she made a big point about saying that we don't actually have 24 independent observations, so that there is some structure in these data that they come from a dish. So it could be that the dish doesn't matter.
Well, what I'm trying to show here is that in some cases, applying generalized linear models might solve some methodological problems. I was asked to help my colleagues with data analysis, and we have 10 accessions of a species collected at different times, different years. And now we want to find out whether climatic conditions in the years when the seeds were collected have any effect on seed viability. But because it's a very rare species, we could use a very limited number of seeds, right? So basically we had one replicate only with 10 seeds. And now you have, if you have 10 years, you have 10 numbers. And you have some values, right? Whatever. And then if you remember, if you want to apply a multiple regression here, right, you need to have at least 10 observations per predictor. If I want to find out, for example, whether precipitation or temperature or solar radiation or whatever has any effect on seed longevity, I would need to have more data, but I don't have it. And then by transforming data to binary variables might increase the number of data points you have. Right, I think I'm going to show it to you better. So now this is the data we're working with. So I transformed the data from proportions to the binary data. I'm fitting here a GLM with binomial data. Then I check the residuals. So, and you can see, well, everything looks fine, no strong deviations. And the point here, because I have now more data and data in a different format, I could fit, this binary model here. And because now I have 259 points instead of 12, I can show that, that my predictions from this model, the model estimates, are more solid and are more trustable. Of course, we can discuss about it, whether it's a correct approach and what is a replicate here. But I think we have discussed this issue briefly. I think it's a field-specific issue. Of course, if you want to run this experiment along a temperature gradient, you would need, let's say, real replicates, not Petri dishes, but different germination chambers, right, which are true replicates. But just imagine you want to use 8 replicates per temperature, then you would need 8 different climate chambers. And if you want to run, I don't know, large screening, you would need, I don't know, dozens and even hundreds of germination chambers, and none of us can afford it, right? I don't know, Terry, what you think about it, but for me, it would be a very nice solution in some cases, when you move from one type of data to another, it would allow you, to do any analysis at all.
I think the point that Adrian was making is that if there's dependency amongst the seeds, then that should be taken into account in the model.
Yeah.
So That was the only point, that by ignoring the underlying data structure, that you can get incorrect inference. And so there was a discussion about pseudo replication. And that was Adrian's question: is a petri dish a sample, or is a seed a sample? So I just bring it up because it ties in with, so we could have another discussion over, how we could take these data, and you could expand the data to be the 0-1 data, but it also include information about the dish, and include that in the model.
And this is actually what Rebecca Miller is suggesting. So, to account for, we could account for those effects by including the petri dish as a fixed effect. If you expect that one particular petri dish might affect, the patterns, or you could include as a random effect to account for this error. My point, and this is probably a kind of personal trauma, if you wish, here. So when I started my PhD, I was told by my supervisor that I always need to have 5 replicates, and I always need to use 25 seeds in each replicate, right? And for example, it would mean that in this experiment, I have 6 temperatures times 8 replicates times 25 seeds. I would need at least 1,200 seeds, to run this experiment. This is, but when you try to collect seeds in an alpine environment, where you can find viable and germinable seeds once in 10 years, like probably a few hundred of them, right? This suggestion didn't really work for me, right? But then I kept coming back to my sites, trying to get enough seeds to run this experiment. But this would be a very nice solution. I mean, like I have said many times, if you deal with a rare and threatened species, so instead of piling up replicates number of seeds you use in your treatments, you could reduce the number of replicates and you could reduce the number of seeds tested, but then you would need to make some data transformations to be able to fit model and get some trustable and reliable results. And this is the point I'm trying to make here. Yeah. All right, I think I have a few lines left. And of course, you could do, is there a question? Yeah, there is a suggestion, so well played to keep each sealed. Yeah, thanks, Lydia. Right, and you could apply here the very same group comparison. You could calculate the turkey, you could compare like I said, the problem with the generalized linear models, with the logistic models, is that the output, you get so-called odds, right? Those logits. Those numbers are not really intuitive and self-explaining to the majority of the scientific community, but there is a very nice patch, so to say, here. So by applying this function, the old good e-means or LSM means package, you can recalculate those logits or odds to probabilities, right? In this particular case, it would mean that the probability of seed germination at the temperature 10.2 would be 0.25, or in all good terms, 25%, right? And of course, you could also use the effects package, to get a quick idea what is going on in your data. Those are data based on your model. Right. I think we just finished half an hour earlier. I think we have now some time to discuss the things we have learned today.
Well, it's true, but we've been going since 8:30.
All right. I was educated at a German university, and if the timetable says that the course should run until 9, No, I'm just kidding. Yeah, you guys look a bit tired and overloaded with all the stuff.
It's been a really lovely big week of conference, so I think everyone's hung in there, which is great. And it's nice to finish with a bit of time for discussion. I popped in the chat. I hope that it's correct, but I think some of that discussion that came up with Terry and Sergey there was really leading nicely into generalized linear mixed models, which we probably would cover in a next session if we had the time. I don't know if Sergey or Terry, if you'd have anything to add to that.
Well, I think Sergey really was very ambitious in covering everything that he did of linear models, having categorical variables as predictors, having continuous variables as predictors, having multiple predictors, covering generalized linear models. I think that you really want to think of it as a taster, and this would normally really be a semester course and not a couple hours course.
Yeah, I have to say that, sorry.
Go ahead.
Yeah. All right, I will finish. So actually, when we were planning this workshop, we expected like 20, 30 people, to come along and discuss the things. But then when we ended up with 114 attendees, we thought, well, it's not really possible to make everyone happy, because we expected that some of you would be like very beginners in R, statistics, some of you would be more advanced students. So we decided, to meet all of you somewhere halfway, right? For the experienced students, we just drill the basics, because I can imagine that some of you are familiar with also some modern and advanced methods like machine learning. But I always have a feeling that we don't drill the basics, right? You listen it in a statistic course, you heard something about residuals that were important, and then you just fit your models, write your papers, and yeah. Yeah, I think it's something like what will change in the years to come. I mean, for those who are really new to the R, I think it's a very good start, right? And also how to specify models, intercept slopes, and things like that. You can always get back, think about your system, about your questions, how to communicate with the software correctly. Yeah, and I have probably one last thing to mention. Mountains. Together with some colleagues from Spain and Italy, we organized a school, seed functional ecology, which will be held next year in January 2022 online. And it's a winter school for early career researchers, seed science, but I mean, they're actually open to everyone who is interested. And it's a 5-day school. So here we cover a lot of aspects of seed ecology and biology, like germination, dispersal, seed banks. Well, we have a kind of extensive theoretical block with lectures, and we also do a lot of stats, right? And so basically the things you learn today, I mean, the scripts we use in this school, but today you had 3-4 hours only to discuss, things in details. But here you have much more time, 5 days to think about it. We have also our wonderful discussions here, and of course, much more practice. So if you're interested, save the date. So it will be the last week of January. Yeah, and you could also stay in touch. There will be some announcements soon about the school.
Thank you for that, Sergey. I wonder if you can paste that link into the chat just so that people can save it if they didn't write it down. So thank you so much for a fantastic day. There's a lot of very positive comments and people who have learned something and had a good day or found it interesting or good to follow. So thank you to all of the presenters for making the workshop that way. It's been great to cover so much, and I personally really appreciated being able to look at these problems with seed specific examples and seed data rather than reading a random textbook example that doesn't apply to my world. So thank you very much for that. For everyone who's still online, we were hoping to just ask one last favor, to ask you to fill in a poll just a couple of questions. It should only take a minute. If you wouldn't mind, this feedback will really help us with future workshops. So I might just give everyone a minute to fill that in. And just while you're finishing your poll questions, just mention one last time that the recordings, we'll just do a bit of editing and then we'll get them up online, and you'll all be sent an update email with a link so that you know where to find those. So anything where you want to watch again or figure out, follow along again, you'll be able to access those. I guess to finish off while people are still voting, Damien, I thought I probably should just throw back to you as if you've got any final parting words for the end of the conference, last session.
Thanks, Lydia. Look, just a big thank you to everyone for sticking in for 5 days. It's been a long week, I know, lots of real intense sessions, but thanks so much for the organising of this workshop. Sergey, Terry, Adrian and Lydia, you've done a fantastic job, and I'm sure a lot of people have got a lot out of it. And like Lydia said, it'll all be available on our website as soon as we can get them edited and posted up there. So thanks so much, and well done, everyone.
All right, I think we've got most people voted. If you've voted, feel free to call it a day and have a lovely weekend. Bye, everyone.